Today we looked at day 1 of Unit 2, and our warm-up had us decide which one doesn't belong on page 81. Take a moment and decide for yourself which one you think wouldn't belong. So here were some of the reasons. A is missing a diagram. Let's see, C was given in inches. D, they did not give you all the side lengths, but they did give you the volume. So it was the only one that had volume. I also pointed out that units for volume would be centimeters cubed. And we talked about the formula for volume being length times width times height. Length times width times height. So then we talked about how to find the volume of each of these shapes. And so if I do the first one for you, 4 times 8 times 10 comes out to 320 centimeters cubed. And if you try example B, it ends up with a different volume than the other 3 boxes. So you might want to review how to find the volume of a rectangular prism. So then our second activity had us taking a 8.5 by 11 sheet of paper and cutting out square corners from each corner. So this example, which I've already folded up, but we cut a 1 inch by 1 inch square out of the corner. This is our next one. We cut a 2 inch by 2 inch square out of the corner, same piece of paper. This was a 2.5 by 2.5 inch. This was a 3 inch, and this was a 4 inch. So we talked about how these were making open boxes. So when I fold up the corners, if I were to tape them together, I would have the open bottom of a box. And we talked about how the volume of the box is changing. So for example, how much could you really fit in a box this size versus inside a box this size versus this was the 3 inch box. How much could you really fit inside a box this size? And which box would have the greatest area? The 4 inch by 4 inch square corners is this really tall, narrow box that could not hold a lot. So we spent some time in our groups filling in this table, and this activity is an anchoring activity for the rest of the unit. So when we cut out a side length of 1 square inch, here is what we're actually doing. So we're taking our, I called this our length. So our length was originally 11, and our width was originally 8.5, because it was an 8.5 by 11 sheet of paper. And when you cut out a 1 and a 1 on either side of your length goes from originally 11 to now a length of just 9. And when you cut a 1 inch and a 1 inch off your width, your 8.5 width becomes 6.5. And when you bend up those sides, because you cut a 1 inch box here, the height of your box is going to become a 1 inch height. To find your volume, multiply 9 times 6.5 times 1, and that came out to be 58.5. Let's do 2 others. Let me just show you for 2 inches and 4 inches. When I cut 2 inches off of either side of my length, it would be 11 minus 2, which would be 7. If I cut 4 inches, 2 plus 2 off my width, which was originally 8.5, I would now have 4.5. And my height is now 2 because my cut corner was 2. 7 times 4.5 times 2 comes out to 63. So that was a little bit better. What about 4? So what if I cut out a side length of 4? 11 minus 4 is just 3 left. 8.5 minus 4 is just a half left. My bending up would be 4. 3 times a half times 4 is only 6. It only has a volume in this little box of 6 cubic inches, not a lot. So the goal is, how could we find the best case scenario of these, the cutout? And so we talked about building an equation, and this is what we put on our big ideas sheet. For the volume of any of these boxes, we originally are taking the length times the width times the height to get the volume of the box. How can we find the length? That's actually 11 minus the two x's, one from here and one from here. How can we find the width? We take 8.5 minus two x's, one from here, one from here. And then whatever the height of our box is, that's going to be x. That's going to be the length of that corner. So in our diagram, that's really where x is. Each of these lengths of these boxes, x by x, is what we're cutting out. How can we figure out the maximum volume of the box? So we are going to plug this equation into our y equals menu of our calculator. So in your calculator, this would be good to practice if you've not done this in a while. 11 minus 2x times 8.5 minus 2x times x. And then if you were to just graph this, you would not see the full graph. All you see is that little part right there. So you're not seeing a volume of up to like 63, because this is a 10 by 10 viewing window. So you go to the window key, and negative 10 to 10 is fine for x, but for your y max, you really should go up to like 100 for your volume. Now when you graph it, you can see the full volume curve. Notice this is not a parabola. It keeps going and it's a cubic function because volume is centimeters cubed. And the best volume is going to occur right at the top of this peak. So if I just kind of move my cursor over, that is around, I don't know, 1.6 or so, and a volume of 65. To get the exact peak, you go to second calculate, you choose 4 for maximum, and you move your cursor to the left, hit enter, to the right, hit enter, and to your top of your peak and hit enter. So the exact maximum is when x equals 1.59 inches, the volume will be 66.1 cubic inches. So somewhere in between here, we had our maximum. 66 is a little bit better than 63. And the other important thing we talked about is, what would be the domain of this function? Could I ever have, for example, a cutout of 5 inches? So the problem is, from the 11, I could cut a 5 and a 5, and I would still have 1 inch remaining. But for the width, if I tried to cut a 5 and a 5, I'm already at 10 inches, and this is only 8.5. So the maximum would be half of your shortest side. So my domain would be x has to be less than 4.25 inches. So 4.2 would be okay, 4 would be okay, but 4.5 inches would be too much, because 4.5 plus 4.5 would be a 9-inch width. And you also obviously can't go less than 0. So when you look at your graph, the only part you care about is from 0 to that 4.25 number. This part of the graph doesn't make sense. You can't have a negative volume of a box. This part of the graph we don't care about. We only care about what makes sense for our domain of our function. So then we did skip 1.3 for today, and we are going to look at examples 1, 2, and 3 together in class to get some understanding of these ideas.